documentation link for that. And then we have a talk from Patrick Gallinari on May 12th. The details for his talk should be coming up shortly. So today we've got Rémi Bardenet. So he is from CNRS at the University of Lille in France, where he's been since 2015. And Rémi's interests include topics like Monte Carlo methods, Bayesian inference, and repulsive point processes like determinantal point processes. And so his talk today is going to be essentially on the confluence of those interests. So as a reminder, please post your questions in the Q&A box during the talk. And we'll stop periodically for short questions, and there'll be a break about midway through the talk for a longer Q&A session. And if any of the questions that are in the text box seem unclear, we may enable audio video just to facilitate the question. All right, so today's talk from Rémi is on Monte Carlo integration with repulsive point processes, and I'll hand it over to him. You have the floor, Rémi.
Thank you, Mike. So hi, everyone. I'm Rémi Bardenet. I'm going to tell you about Monte Carlo methods with repulsive point processes, as Mike said. Thanks a lot for inviting me to talk about this. Always happy to talk about DPPs and repulsive stuff. The subtitle is actually from random matrices to kernel quadrature. So you'll see that I've organized the talk so that it's actually a path from a puzzling result in random matrix theory, and it ends up with techniques to actually perform Monte Carlo methods in reproducing kernel Hilbert spaces, so spaces of functions where the smoothness is governed by a kernel. So this is going to be the talk. I'm with CNRS, and this is research funded both by the INR and the ERC. So let's go. So I'm going to start with a few notations on numerical integration. I guess since this is the Laplace seminar, Laplace's Demon seminar, you guys are all up to date with the latest methods, including the latest two talks by Christophe Andrieux and Anthony Lee on numerical integration. But just to fix the ideas and fix notation, I'll have one slide in the prologue. Then I will tell you about this example, this puzzling random matrix example that Adrien Hardy, a good friend of mine, actually showed me one day, and this actually triggered my interest in determinantal point processes and negatively dependent measures otherwise. Then the third part is going to be about taking this random matrix example and making it a Monte Carlo theorem, making it a theorem about Monte Carlo integration in any arbitrary dimension that you might want to integrate a function in. And this is going to be Monte Carlo with DPPs. DPPs are determinantal point processes, and they're a specific kind of repulsive point process. So I'll tell you what DPPs are in more detail later on, but think of a bunch of points in RD that repel each other. Think of electrons repelling each other with a Coulomb interaction, for example. So this is going to be what I call a bottom-up approach, because we actually went from this puzzling random matrix example and tried to make it a Monte Carlo integration result. But the last part, which I call DPPs lead to tight rates in RKHSs, is going to be about the top-down approach to the same problem. So basically you ask, in this last part, you ask, okay, what's the most natural space of integrands that DPPs would be good at integrating? And the answer, one natural answer, is reproducing kernel Hilbert spaces, so spaces of functions where the smoothness of the function is governed by a kernel. And we'll see how you can actually perform very efficient quadrature with DPPs in RKHSs. This is the top-down approach. Okay. So numerical integration. So for the length of this talk, I'll use f as an integrand, and the measure I want to integrate against is mu. So I want to compute integral of f d mu. So mu is a positive measure. It has a finite mass. It's a nice measure that you want to perform integration against. And quite often, whenever I will need a density, I will assume that mu is a measure on RD with the density with respect to Lebesgue, and I will then denote the density by omega. So what I want to compute is the integral of f of x, omega of x dx. And I want to approximate this by a finite sum. I want to perform numerical integration. So I will approximate this by the sum over n terms. Capital N is always going to be the number of nodes I will try to stick to that notation. Number of nodes in my quadrature. The nodes are the xi's, the points where I actually evaluate my integrand f, and the wi's are the weights. Okay, this I will call them the weights. Monte Carlo integration, important sampling, MCMC, SMC samplers, you name it, are all methods to actually choose the nodes randomly and perform the computation for the weights, wi. Quite often you take wi to only depend on the position of xi. This is the case in importance sampling, for example. But there are also cases where you introduce some dependence by taking wi to depend also on the other nodes, which I denote here by x minus I. This is the case in self-normalized importance sampling, for example, okay, where you have to renormalize the weights by the sum of all the other weights, by the sum of all the weights, so you actually depend on the other nodes. Okay, the typical error, typical result that you would see in a Monte Carlo textbook is that the root mean square error is of order 1 over square root of the number of nodes. Okay, you measure the error by looking at the difference between the integral of f d mu, what you actually want to compute. Think of Bayesian inference. Bayesian inference is full of computing integrals of a loss function with respect to a posterior measure. So integral of f d mu is your target integral, is what you want to compute, and you replace it by this discrete sum, this finite sum of wi f of xi, and you square this, you take the expectation, and you take a square root, and usually what you're able to prove is that this goes down at the rate 1 over square root of n, okay, n being the number of evaluations of the integrand. Now, this is obviously slow. Most often you cannot actually, there's actually not many other options, but there are cases where this slow rate is really an issue. Think of a biologist, a cell biologist. He models the electric response of a cell to stimuli by he has a likelihood for the parameters, the conductances of the different ion channels in his cell, and he wants to model he wants to infer these parameters given some data about the electrical response of a cell to different stimuli. Now, the evaluation, a single evaluation of the likelihood in this kind of experiments takes minutes. So it's obviously completely unthinkable to run Metropolis Hastings, for example, for 1 million iterations, unless you have 2 years to wait for the answer. So there are applications where this, the cost of evaluating f, or the cost of evaluating omega, the density of the measure mu, is actually so big that you really need to think carefully about what m to use. This is much akin to the problem of experimental design in linear regression. If evaluating f once is actually costs you either a lot of money or a lot of time or a lot of CPU time, then you might actually want to choose the xi's where you evaluate the response wisely. Okay, so let's see how we can actually choose the xi's to take this rate down. There's several options, but I will show you an option that actually originates in random matrix theory. Okay, let's take UN, the group of unitary matrices. So UN is just a set of complex matrices such that A times the transpose of the conjugate of A is actually I, the identity matrix, okay, unitary matrices. Now there's a uniform measure on UN. It's called the Haar measure. So there's a natural equivalent to the uniform measure on UN, and you can actually draw from it. It's not really hard. It uses the QR algorithm. You can draw uniformly on UN. So trust me on this. Now, because you've drawn a unitary matrix, the spectrum of the matrix is actually on the unit circle in the complex plane. So you can denote the eigenvalues by e to the I theta j. And from now on, I will work with the arguments theta j of these eigenvalues. Now, Johansson proved that for any f smooth enough, and I will tell you in a moment what smooth enough means, the sum of f of theta I, remember theta I is they are the arguments of the eigenvalues of u. So you take any f, any test f smooth enough, and you sum f at the theta i's. Now you subtract n times the integral of f with respect to the uniform measure over the circle, and you have something that converges in law to a Gaussian. So this is surprising for a few reasons. The first reason is that the sigma squared of the Gaussian is quite nice. It's given in this pink expression that I've written at the bottom of the box, and it's a measure of the decay of the Fourier coefficients of f. Okay, the faster the Fourier coefficients of f decay to 0, the smaller the asymptotic variance. So it's quite nice to see, an inherently analytical quantity appear in the asymptotic variance. But what's actually most puzzling about this theorem is that the quantity that converges to the Gaussian is of order 1. That means that if I divide it by n, I obtain an estimate of the integral of f with respect to the uniform measure over the circle that with an error that decreases as 1 over n. Okay, and 1 over n is much smaller than 1 over square root of n. So you're happy as a Monte Carlo person. You're happy when you see this kind of theorems. You think, okay, there might be something to do with this. So what happens under the hood? What happens if you look at the left panel of that plot? I've drawn a couple of points IID from the uniform measure over the circle. And on the right panel, I've shown you the arguments of I've showed you a couple of eigenvalues of a unitary matrix drawn from the Hall measure. So this is actually an example of theta i's. The angles, the arguments of these points are actually theta i's in the previous theorem. And you can see that the points on the right panel are much more evenly spaced on the circle than on the left panel. Both have the same intensity, okay? They're marginally very similar, but the correlation between the points on the second panel is much stronger. It's actually anti-correlation. They're actually pushing against each other, and since there's the circle is compact, there's not much space where they can flee. So they actually arrange themselves in a very regular grid on the circle. In this sense, if you redraw from the same distribution over unitary matrices, you will get something very similar to this because the pattern is very constrained. And this means that if you integrate a smooth function over this point process, then you will get a result that doesn't vary a lot from realization to realization. That means a small variance. Okay, and in a sense, repulsiveness here acts as a powerful inbuilt control variate. So for functions that are smooth in the sense that their Fourier coefficients decrease fast, then this set of eigenvalues is a good set of quadrature nodes. That's what Johansson's theorem tells us. In this particular example, I've used the word Fourier maybe a couple of times already. You'll see that this particular example is tied to the Fourier basis. And in the rest of the talk, we'll see how we can actually generalize this. Okay. So how do we take this theorem and make it an integration algorithm? First, we have to get rid of the random matrix setting, okay? Because matrices have eigenvalues in R or C, and we want to integrate functions in the whole of RD. So we have to get rid from the random matrix setting, and we have to take in the proof of Johansson, we have to keep only the terms that cause the fast decay of the variance and remove the random matrix source. It turns out that what makes the preceding theorem work is combinatorial arguments related to determinantal point processes. Determinantal point processes are an example of repulsive point process, which I'm going to introduce right now. And this is what we've conserved from Johansson's theorem. I will actually not need to introduce projection. I will actually not need to introduce general DPPs in that talk. What I will introduce is projection DPPs. Projection DPPs are much easier to introduce because I can give them to you using a regular PDF with respect to an ambient measure mu. So let phi k be an orthonormal sequence in L2 of mu. Remember, mu is the measure you want to integrate against. And you take L2 of this mu, and you take an orthonormal sequence in L2 of mu. Now, take the following kernel, capital K of xy, is the sum of phi k of x, phi k of y for the first n orthonormal functions phi k. Okay, So this is a projection kernel. This is the kernel of a projection operator onto the span of the first n phi k's. Now, this is a definition proposition, if you want. What I'm saying in this blue box is that the PDF that's written in this play style here, 1 over n factorial times this big determinant in pink times the product of d mu of x1 to d mu of xn. This is actually a PDF. This is well normalized. And I'm defining a DPP, a projection DPP here with kernel k and reference measure mu to be the set, the unordered set of points x1 to xn when I draw x1 to xn proportional to this density. Okay, so you have to trust me that this is a density. This comes actually from the fact that the phi k's are orthonormal, or you can do the computation if you want. This is well normalized. And if I draw x1 up to xn and I forget the order, I get what we call a projection DPP with kernel k and reference measure mu. Okay. What do points drawn from such a DPP look like? They look like independent points drawn from mu. Okay, that comes from the product of d mu of x1, d mu of xn. And then there's this penalization here, this big determinant. Now, this big determinant here, there's many ways to interpret it. Maybe the most immediate way, if you think of k as being a decreasing function of the distance between xi and xl, you will see that this determinant is small when you have two columns of this Gram matrix, which are collinear, and they will tend to be collinear when you have a small distance, a small Euclidean distance between xi and xj. So you will favor configurations of points where the different xi's are actually far from each other. So this intuition is a first rule of thumb, and it's only valid if you have your k that is a function of the distance between xi minus xl and the Euclidean distance and a decreasing function. So a more general intuition about this is maybe to see that this pink term is the squared volume of the parallelotope formed by the functions k of xi dot. Okay, to each xi, you associate a function, k of xi dot. It's called a feature function in machine learning. And if you look in the span of these n feature functions, that's a finite dimensional space, which I call the feature space. Now, this big pink determinant is just the volume, the squared volume of this parallelotope spanned by the k of xi dot. Okay, this is a property of Gram determinants. Now, that actually gives us maybe a more general intuition that points that are likely to appear under a DPP are points that correspond to feature functions that span a large volume. Okay, and that's in general, that's I think that's the right intuition to have. Okay. If and only if you have already seen finite DPPs in machine learning, you can connect what you have in mind to the above definition. Just take mu to be the counting measure, and you will recover the definition of correlation of the correlation kernel of a DPP. If you've never seen point 1, just don't bother for now. But I just want to make it appear for people who maybe have known DPP through this literature. The second bullet here is a consequence of the definition. It's that the marginal of any point in the pattern is actually what's called the diagonal of the kernel. So it's k of xx times d mu of x, normalized by this 1 over n. So that actually you can build a quite natural estimator of the integral of f d mu that will be unbiased using importance sampling. So you sum f of xi, okay, f evaluated at each of the points drawn from your DPP, and you divide each evaluation by the k of xi, okay? Because the marginal of any point is actually proportional to k of xx d mu of x, you get an unbiased estimate of the integral of f d mu. This unbiased estimate, if you're familiar with Gaussian quadrature, it's exactly Gaussian quadrature. But in Gaussian quadrature, the xi's are not random. They're actually related to the zeros of the orthonormal polynomials that you put in K. So whenever you choose to, my phi k's here above, to be orthonormal polynomials in 1D, so mu is a measure on the line, and phi k's are orthonormal polynomials, you actually get exactly the same estimator for your Gaussian quadrature, except that now we're using a sample from a DPP instead of zeros of orthogonal polynomials. It turns out that you can show that samples from a DPP built with orthogonal polynomials are quite close to the zeros of orthogonal polynomials. So this all points out to the same fact that DPPs are a kind of randomization of Gaussian quadrature. What's good is that DPPs are naturally defined in any dimension. It's the only thing that you have to input is a sequence of orthonormal functions phi k. You don't have to resort to all of the tricks that are common to make Gaussian quadrature multidimensional. And last point 3 of my bullet list here, I've already mentioned it, a natural choice, at least if you're into analysis, a natural choice that you might want to try from the beginning on is to take phi k's to be orthogonal polynomials with respect to mu. It's also a natural choice if you want to perform numerical integration. Why? Because orthogonal polynomials have this property that they tend to oscillate a lot in regions where mu puts a lot of mass, and this will actually have as a consequence the fact that the DPP will put a lot of points where mu puts a lot of mass. The repulsion between the points is lower when you're in high mass regions under mu. And this is quite desirable because what you want from a good integration algorithm is that it puts a lot of points where mu has a lot of mass and where the integrand is likely to oscillate a lot, because you want to capture these oscillations. Whenever mu is close to 0 or f is really flat, then maybe a few points are enough to capture what's happening there. So this is just my hand-waving justification for point 3, that it's quite natural to look for orthogonal polynomials and build the phi k's using univariate orthogonal polynomials. I will not detail this multivariate construction, but I will show you an example of a sample, maybe so that you can get the feeling of what these DPP samples look like. Here on the left, again, I've shown you an IID sample from the product of these two grain marginals. Okay. So this is an IID sample. You can see that the points concentrate on the right of the plot because the x marginal is, the x marginal is actually larger there. And all the points have the same, correspond to the same kinds of disk, because I've actually, I don't have to normalize the points here to get an unbiased estimate. On the right panel, I've actually shown you an example of a DPP sample that I've built using orthogonal polynomials with respect to the two grain marginals. It's called an orthogonal polynomial ensemble. And if I draw from this point process, if I draw from this projection DPP, I actually get a point pattern that looks like the one on the left panel, but with more repulsion. I have less clusters on the right than on the left. What you can also see is that the points explore more. It's the same number of points on the two panels, but you can see that there's a few points of the DPP that go pretty far away to try to explore the support in a more organized manner, and they repel each other. You can also see that the points on the right panel correspond to larger disks, because I've actually set the area of the disk here to be proportional to 1 over k of xi xi. So this is the weight in the unbiased estimator that I showed you on the previous slide. And you've got weighted histograms showing you a good agreement with the marginals. But this is just so that you have in mind the difference between a DPP sample and an IID sample. So more repulsion, although the repulsion is doesn't have to be the same in all regions of the space. In particular here, you have more repulsion in areas where the target mu puts little mass because of this marginal here. And then you have repulsion here in the bulk of the distribution where you want to have more points. And the DPP actually tells the points not to repel themselves too much in this area. Okay. So we wanted to we wanted to generalize Johansson's random matrix result to a general Monte Carlo theorem, and this is what we obtained. So again, assume mu as a density omega with respect to the Lebesgue measure on R to the D. We will actually work with compactly supported measures here. So everything is on -1, 1 to the D. We will also assume that omega is separable C1. We have a couple of assumptions to make here that we will actually relax on the next slide. And basically we draw x1, xn from the corresponding DPP built using orthogonal polynomials. Okay, I'll answer the question of Amiros in a moment. I will pause after the next slide because it's going to be a natural pause in the talk. If x1, xn stands for the associated multivariate OP ensemble, okay, so the corresponding DPP, then for every f basically C1, and I also have to assume that it vanishes close to the border. There's a missing D exponent here. I get the following CLT. So if you've been patient enough to go through the assumptions, now is the reward. We have the unbiased estimator that I showed you before. Okay, sum of f of xi divided by the marginal of xi, k of xi. This is a good approximation of the integral of f d mu. And how good? I have to scale it by this this amount to actually make it big O of 1. So this converges at the speed square root of n to the 1 plus 1 over d. And this converges to a Gaussian. So two observations here. The asymptotic variance of the Gaussian here is also a measure of the decay of the Fourier coefficients of f. Although now I have f times the density of mu, and I have the previous section. All right. Yeah. So this is the theorem that I was telling you about. So couple of assumptions. Maybe the most interesting ones are that the function we integrate has to be C1, and omega, the density of the target measure, has to be C1 and compactly supported. The function also has to vanish on the border of the interval, and I'll tell you in a moment why. This is the unbiased estimate that I told you about before, and this is the integral we want to estimate. And you can see that the speed here is slightly faster than the traditional Monte Carlo rate. By slightly, I mean 1 plus 1 over d. So d is the ambient dimension. So you're happy because it's faster than Monte Carlo. And of course, if d equals 1, like in Johansson's result, this is square root of n squared. So this is n. This is really fast. But obviously in Monte Carlo, in the Monte Carlo world, if d equals 10 or if d equals 100, then this is just as good as plain Monte Carlo. So it's in a sense, the result is interesting, but not DPPs. Projection DPPs are not repulsive enough to integrate generic C1Fs. The other remark, sorry, switch slides. So the other remark I want to make is we've preserved the fact in Johansson's result that omega squared, the asymptotic variance, is actually measuring the decay of the Fourier coefficients of f. This time, it's not only the Fourier coefficients of f, it's f times omega, the density of mu, and you have to divide it by an equilibrium measure, which is a beta 1/2 measure, which might, I haven't read the Miros' question in full, but you might not be surprised to see this equilibrium measure of the unit cube here. So again, I think what I like in this result is the fact that the asymptotic variance, the asymptotic variance is a really analytical quantity. There's no autocorrelation time. There's no chi-squared distance. There's nothing statistical that introduces itself in your measure of error. The measure of error is a purely analytical quantity. So in a sense, the DPP doesn't disturb Gaussian quadrature. Is what I'm saying. The other remark is the rate, which is faster than Monte Carlo, but not as fast. So to make it faster, you need either more repulsion or you need to restrict the f's that you integrate. You can also check. There's a preprint by Kerjoli, Mazouillet, and Amblard. They basically showed the same theorem, but they wanted to remove the 1/k of xi weights, which forced us to have FC1. And so there's a very specific DPP for which you can actually remove this and still prove the theorem. And this allows you to take the assumption on F down. Another remark that this crowd will immediately make is that, okay, to sample your DPP, you actually, even to define your DPP, you needed the orthogonal polynomials with respect to mu, the measure with respect to which we want to integrate. This is a lot to ask, right? Because if you have the orthogonal polynomials, you have all the moments of the target function, of the target measure. And there might not be many Bayesian applications where you know all the moments of your posterior and you want to estimate some other integral. So an immediate question is, can you do all of this? Can you keep this theorem valid somehow without requiring the moments of mu? And the answer is yes. And this is maybe a surprising feat of DPPs in orthogonal polynomials. Actually, you can write the same theorem by putting all the assumptions on a measure Q for a proposal. So you take another density Q on which you put all the assumptions of the previous theorem. You take the kernel that corresponds to the orthogonal polynomials with respect to Q. Okay, so Q, you might as well choose something very easy to like a product of Gaussians, so that you have the orthogonal polynomials. And you draw x1 to xn from the DPP that corresponds to this kernel and the reference measure Q. So far you have done nothing with respect to mu, your target density. And then all you have to do in the spirit of importance sampling is to add these weights, omega of xi, the target density divided by Q of xi, the proposal density, and you maintain exactly the same CLT. In particular, the asymptotic variance is unchanged. It still only measures the decay of the coefficients, the Fourier coefficients of f times omega divided by this beta PDF. So I think this is quite interesting, and this is really the magic of orthogonal polynomials and universality results for orthogonal polynomials here at play. The asymptotic variance is unchanged. You don't suffer, asymptotically at least, you don't suffer from not having used the target pi as proposal. I think this is quite nice. Okay, I'm gonna pause here to maybe take a couple of questions on this first part of the talk, and then I'll spend 15 minutes finishing the talk if that's okay.
So Rémi, I think I've been unmuted, so I can ask you directly.
Yeah, sure.
I think, yeah, this is really beautiful, this kind of stratification. And my first question was the one that you just answered. I mean, I was basically pointing out that in your figure, these densities look like rescaled betas for which you have the orthogonal polynomials, but I was asking how is it to get in general? So that you answered. Can I ask you a quick question about this asymptotic variance? I mean, it is very, in the previous slide, you have this nice analytical expression, and I agree that's a very beautiful expression. But the fact that there is nothing statistical in this expression, isn't this also a problem? I mean, how can you calculate this? How can you estimate this from, let's say, data, etc.?
Yeah, that's another problem, and I don't have a good answer yet. We'll see in the rest of the talk. I'll give you another kind of result where maybe the bound on the mean square error is a little more tractable. But I don't know yet, like how to estimate this in practice.
And just
more efficiently than actually computing the target integral.
Just to take advantage of the fact that I have this unmute, can you give any intuition why the asymptotic variance in your other result does not depend on the discrepancy between omega and?
So there's actually this basically asymptotically under loose assumptions on mu, all the orthogonal polynomials look the same. They look like the Chebyshev polynomials. And one thing that you can actually prove is a result by Totic that says that k of xx times mu times omega of x, so the diagonal of the kernel, k of xx times omega of x, divided by this mu ek, this equilibrium measure, this beta 1/2, 1/2, I think that converges to 1. for a wide class of mu's. So basically, the density of the particles will always look like this beta 1/2, the marginal, whatever mu, whatever the orthogonal polynomials.
Okay, thank you very much.
Well, you're welcome. It's quite puzzling, but yes, there's this universality of Chebyshev polynomials under quite loose assumptions on mu, and this is what's at play behind this independence. Any other question on DPPs so far?
I don't see any. I think we can continue and then pause for more questions at the end.
All right, excellent. So this we've covered, this important sampling version. So is it okay if I still talk for 15 minutes? Is that right, Mike?
Sure, that's fine. Yeah.
All right, cool. So the last part is, okay, now we have our CLT, but we're not too happy because we wanted a fast rate. Square root of n to the 1 + 1/d is not very impressive. So let's see what we can do. One avenue would be to make the DPP somehow more repulsive, maybe play with a kind of temperature on the determinant. This is something that we haven't explored yet. Another avenue is, okay, let's make assumptions on the integrand, and let's try to find the right assumption to make the rate fall down at a faster rate. So you're looking for an assumption on integrand f, such that f would be integrated well by a DPP. A DPP is kind of the kernel machine of point processes. It's a point process where the repulsion between the points is governed by a kernel. So ideally, intuitively, you'd like a function space for the integrands where the smoothness of the function is governed by a kernel. Okay, and that's a natural answer to this is try and take reproducing kernel Hilbert spaces. So there are spaces of smooth functions governed by a kernel. So I will denote them by F for function space. And little k will always be the kernel of my RKHS. An RKHS, if you've never seen it, it's you take the sums of the finite sums of weighted sums of feature functions k of xi dot. Okay, so think of k as a Gaussian kernel. This is just a mixture of Gaussians, okay, a sum of Gaussians, but you're allowing the weights alpha I to be any real number. And then you're going to take the completion of that set of linear combinations. You're going to take the completion with respect to a very specific norm, the norm that is given by the inner product in pink here. So you want the inner product of k of xi dot with k of y dot, the two feature functions, to be k of xy, okay? You want to be able to use what's called the kernel trick in SVMs, support vector machines. So you want to be able to compute the inner product of two feature functions by the kernel k of xy. And if you do so, if you complete the set of linear combinations with respect to that norm, then you get a Hilbert space. And under quite loose assumptions, your function space f is going to be included in L2 of d mu, and it's going to be densely included. If you make these assumptions, then you have an orthonormal basis En of L2, and you have a sequence sigma n that goes to 0 of positive values of a positive sequence sigma n that goes to 0, such that k of xy is actually pointwise equal to the following limit. It's the sum of the sigma n times En of x, En of y. So it looks like you've diagonalized your kernel using an orthonormal basis En of L2 of d mu, and this is called a Mercer decomposition. So you might have seen this if you've studied SVMs, for example. So under quite general assumptions, I can diagonalize my k, is what I'm saying, and I have the following expression: sigma n times En of x, En of y, and I take the sum of this. Okay, if you've made these assumptions, actually you can check that if you take a function in L2, you have a necessary and sufficient condition for this function to be in the Hilbert space f, and that condition is that you need the generalized Fourier coefficients of f in a product En. You need this to decrease at a fast rate, and the rate is given by the eigenvalues of the kernel. So this is the sense of this pink expression. the Fourier coefficients in the sense of f in a product En, they have to decrease fast enough such that this sum is actually converging. Okay, so you can feel already that there's a notion of smoothness in this space that will be governed this time by the eigenpairs sigma and En of the kernel. Okay, the other interesting thing about RKHSs is that quadrature in these spaces is actually equivalent to it's not equivalent, but it's you can bound the quadrature error by the approximation error of mu g. So what I'm saying is the following: it's this equation 1. If you want to integrate f d mu, and there's an additional degree of freedom that I call g after a paper by Bach. So g is in L2 of d mu, and you have this additional degree of freedom. You want to integrate f g d mu. You want to integrate this using a finite number of evaluations of f. And this error is controlled by a term which is the norm of f in the Hilbert space times this pink term here, which is an approximation error. Okay, it's measuring how well you approximate mu g. Mu g is given in the line after that, after equation 1. It's the embedding of g, which is in L2, into the RKHS f. So it's a way of embedding any function of L2 in the RKHS. And you want to approximate this mu g by your finite sum of feature functions with the same weights that you use in your quadrature formula. So what I'm saying with this equation 1 is just that if you control the approximation of g by your weighted sum of feature functions, then you have a control on the quadrature error in RKHSs. So it's a nice way. An RKHS is a nice way to replace quadrature with geometry and approximation. This mu g is called the mean element of g. You might have seen this in talks on RKHSs. But think of it as an embedding of a function g in L2 into an RKHS. Okay. And once the nodes x1, xn are known, this is my last bullet on RKHSs. Once you know the nodes, if they're in general position, then minimizing the right-hand side of equation 1, minimizing the pink term in 1, is actually boils down to inverting an n by n matrix. So if you know the nodes, optimizing over the weights is easy. That's the other nice thing about RKHSs. So all you need to do if you want to perform quadrature in an RKHS is to do approximation of mean elements, and you only need to take care about the nodes because the weights are easy to compute. That's the lesson of that talk. So how do we choose the nodes? The first thing we wanted to try, obviously, because we're DPP aficionados, is to remember the Mercer decomposition of little k, the RKHS kernel. We take the first n eigenfunctions of this kernel and we project onto it. So we take the first bullet of my green box, capital K, the kernel of the DPP. Capital K is always going to be the kernel of the DPP, little k, the kernel of the RKHS. We want capital K to project onto the first n eigenfunctions of the RKHS kernel. That fits into the definition of projection DPP that I gave you earlier today. The definition was actually equivalent to sampling x1, xn from the density given in the second bullet of my green box. And the third bullet is saying, okay, once you have sampled the nodes, just solve the linear problem for the weights. I told you the weights is easy in kernel quadrature. You only have to care about the nodes. Now, our PhD student, Ayub Belhaji, was able to prove that if you assume that G has a small norm, a small L2 norm, at least it has to project onto the first eigenvalues with a norm smaller than 1. And if you denote by Rn in green, the tail of the eigenvalues of the RKHS kernel, okay, remember n is the number of quadrature nodes. And here you sum the eigenvalues starting from the one immediately after the number of nodes. Then, in expectation under our DPP, the quadrature error, at least the bound on the quadrature error, which is this approximation error for mean elements mu g, is smaller than the sum of two terms. There's the pink term, which is the one that you expect to see, 2 times sigma n plus 1. You basically want to do something that is akin to PCA, so you kind of expect sigma n plus 1, the first eigenvalue after the number of nodes, to show up. What you don't want to show up is the green term. So it's a term that depends on the tail of the eigenvalues. And so you're not really happy because you want only to have the pink term, and the green term is only going to be negligible if you have some assumptions on the decay of your kernel eigenvalues. So then we asked, okay, Ayub Elhaji, how do you prove the same result but with only sigma n plus 1? And he's smart, so he managed it. And he said, okay, what I would have had to do is to start with not the DPP, but with what's called volume sampling. Okay, it's a natural continuous equivalent to something which in the discrete, in randomized linear algebra is called volume sampling. You have to sample x1, xn proportionally to the gram matrix, this time of the RKHS kernel. Okay, and there's no guarantee that this is well normalized, so you have to put a 1 over z in front, and this z is actually potentially hard to compute. But if you could sample from this density, the first bullet, which is not a DPP, you can actually show it's a statistical mixture of DPPs, but it's not a DPP itself. If you can sample, and if you can again solve the linear program for the weights, told you this is easy, then you'd have the following guarantee. The expectation of your approximation error in green, right? Remember, this is the term that controls the integration error in an RKHS. The expectation of that green term is this time smaller than sigma n, what you expect, the nth eigenvalue of the kernel. You'd actually expect sigma n plus 1, but here you get sigma n times 1 plus a small positive something. And this small positive something, it turns out that it's bounded in every RKHS that we know and for which we know the sigma, for which we know the eigenvalues. So we haven't proven it yet, but we believe this is this beta n is bounded for under very loose assumptions on the kernel little k. But for every RKHS for which we know the eigenvalues, this is bounded. So we're happy with this term. We're happy with this result because it actually is tight. It's tight in the following sense. It's the last bullet on the slide. It's a result in n-width theory by Pincus that says that my green term in my blue box is actually the infimum if I take y in capital Y equal to the span of the feature functions k of xi dot. It's actually the infimum of this RKHS norm here. And remember, my bound here is independent of G. So if I take a supremum over G of this green bound, and I even look for the best subspace, I do not even limit myself to spans of feature functions, but I look for the best subspace of dimension n, then the best thing I can do is actually sigma n plus 1. So with my sigma n times a constant, I really have the right rate up to 1 index in the eigenvalues. So this is, I think this is really neat because before that, you didn't have any general result for integrating in RKHSs. You had specific RKHSs like sub F. You knew tailored quadrature designs that reached the lower bound, but we didn't have a construction that only depended on the kernel K of the RKHS. So this is one. Now there's many open problems, and I'm happy if you have ideas about this. So I can add a bullet for Ramiros is how to actually estimate sigma n if we don't know the eigen, if we don't know the eigen decomposition of the kernel. But that actually might be open to statistical techniques and geometry. I think this is more tractable than the asymptotic variance of the DPP. There's the robustness to the RKHS hypothesis. We're not really happy in practice. I mean, if you're doing an application of Bayesian inference, you never know whether your target is in an RKHS and your F is in an RKHS more than the pi. So we want to be robust to the RKHS hypothesis, and we have hints. You can look at the latest paper by Ayub Elhaji. There's hints that volume sampling is more robust to the integrand not being in the RKHS. So misspecification of the RKHS. Volume sampling is more robust than the DPP. Or this is related to how you would actually choose the kernel K to integrate a given function. There's the practical relevance of the RKHS hypothesis. So when is it okay to assume that your target is in an RKHS? I told you there's this additional degree of freedom, this function G in L2 of mu, which you actually try to approximate in your RKHS. What should it be in practice? There's this degree of freedom. Can it take one part of the integrand, one part of the target measure in Bayesian inference? Are some G's easier to approximate in the RKHS than other G's? And how should you split your problem into an F and a G and a mu? That's an open question. And how do we efficiently, I mean, if volume sampling is the answer, how do we efficiently sample from volume sampling without having the Mercer decomposition of the kernel? So I didn't tell you too much about sampling, but sampling projection DPPs, we can do this in time roughly cubic in N. If I neglect like rejection sampling routines, but that's doable. But that's doable if I have the spectral decomposition of the kernel. What's good with the volume sampling is that it doesn't look like you could sample from it if you had the spectral decomposition, but because it's only proportional to the determinant of the gram matrix of the RKHS kernel, it's actually amenable to MCMC. What's the best MCMC kernel to actually sample from this continuous volume sampling? This is something that we are looking at the moment. And that's it. So wrapping up, random matrix theory provides a large DPP toolbox. You can obtain CLTs. So there's our work, and there's this preprint by Kersholi et al. Volume sampling yields tight MSE bounds in RKHSs. If you've wondered whether all of this is similar to experimental design for linear regression or column subset selection for if you want to do a feature selection for in linear regression, you're right. I mean, this is a kind of continuous equivalent to column subset selection that we've covered today. It's surprising though that, so we've also worked with the same PhD student on column subset selection. And it turns out DPPs and VS volume sampling yield similar bounds. And by similar, I mean that the two have similar bounds. Whereas for DPPs in kernel quadrature, so far, we haven't been able to suppress this term that depending on the tail of the eigenvalues that I showed you. In practice, in experiments, in toy experiments, the green term doesn't show up. So it's likely that it's just us. We haven't been good enough at proving this, but anyway, you can check out the work on column subset selection if this was of interest. And sampling DPPs and volume sampling, that's the focus of intense research. So you can check out the thesis of Guillaume Gauthier that has everything up to date in 2020. And the Python toolbox DPPy has all algorithms for finite DPPs and a couple of algorithms for continuous DPPs, including the ones that I've showed you in this talk. So DPPs and mixtures of DPPs yield fast Monte Carlo error rates. That's my take home message. And data analytic assumptions with no design. I think that's for Monte Carlo purposes, I think this is the nicest thing is you make an analytic assumption on F. This translates into a kernel K that will tell you how your quadrature nodes are supposed to repel. And I think this is the key for, this is why the measures of error, the asymptotic variances, the mean square error, like are really analytic quantities, is that you've actually introduced exactly the right repulsiveness for the problem at hand. 2 announcements. So I have PhD and postdoc applications open, so you're very welcome to apply. You can find there's actually an opening for a PhD right now with Subro Ghosh, probabilist in Singapore. So feel free to check it on my website if you're an aspiring PhD student. And we're gonna have, if you're into Bayesian learning, there's a summer school on end-to-end Bayesian learning. I think David posted the link in the chat. So it's in October, and as we were discussing with David and Mike, it's likely to be maybe, I mean, if we're optimistic, it could be the first event where we meet in person. So that'd be really nice. All right, thanks for your attention, and I'm happy to take any questions you may have.
Thanks, Rémi. Great talk.
Thanks.
Let's see. So I've got a question here. I don't know if you can see it in the Q&A box from Andy Wang.
I can't see the Q&A box yet.
I'll read it out to you.
Chat.
So it's,
I can see.
he says, related to the first part of the talk, I believe that the eigenvalues of random Hermitian matrices also exhibit a repulsive effect, except on the
Yeah.
real line, not the circle.
Yes. Yes.
Could they similarly be used to inspire a numerical integration scheme?
Yes, to me, I see. I chose this one on unitary matrices as because I think it's an example that you can. That it's one illuminating example, but the one you mentioned, for example, if you put Gaussian, you put little Gaussians, little complex Gaussians, IID, into a matrix, and then you make the matrix Hermitian by symmetrizing it, and then you take the eigenvalues of that matrix. You will end up with a DPP on the line because the eigenvalues of a Hermitian matrix are real, and you will end up with a DPP. And this is actually an example of DPP that is a subcase of the theorem in dimension 1 of the theorem that I showed you, of R theorem. So all of these examples are actually similar. The one you're mentioning is actually the stochastic equivalent in my mind. It's the stochastic equivalent to Gauss-Hermite quadrature.
Okay.
We've seen also Gauss-Jacobi quadrature in the talk, as Amiro said. So it's all Gaussian quadrature for me. It's just the reference measure that changes.
Okay, cool. Let's take maybe at least one more question. I think we can allocate a few additional minutes because we had some technical difficulties earlier. So this is from Jose Gallego Posada. He's saying, maybe I missed your remarks, but in the first MC theorem you mentioned that it was necessary for the function to vanish around the edges, -1 plus minus epsilon
Yes.
power d of the hypercube. Can you comment on this again? And does this relationship grow with the cursive dimensionality as d grows?
All right. So let me go back to that slide, and I hope the slides don't freeze. If they do, it's not too bad. So this is, here I'm on my slide that says the first Monte Carlo result, where we have this assumption that the integrand f has to vanish at the borders of the hypercube. So there's a missing d, exponent d. But this is related, I've colored this in pink because this is related to the 1 over k of xi that I've also colored in pink. The fact is, I've told you these orthogonal polynomials, they tend to oscillate a lot. And 1 over k is a function that is very badly behaved at the borders of the hypercube. To control the error introduced by this, basically we have in the paper, you can check that there's a first CLT on the sum of f of xi, and this one is easy. I mean, easy. It's not easy to prove, but you don't have to make any strong assumption in f. This assumption that f vanishes at the border is to help us control 1 over k at the border. It's related to the result I was mentioning to Amiros earlier, that k of xx omega of x divided by this equilibrium measure, the beta 1/2 converges to 1. This is actually true on every compact set within the interval, included in the interior of the interval. This is not true at the border. And the behavior at the border is not very well understood. And at some point in the proof, we abandoned understanding it, and we just assumed FC1 vanishing at the border. And that suffices for the proof. I think if you look at Kerjeli's result, Kerjeli, Mazoyen, Amblard, the one I'm citing at the one I was citing in the talk, and that's cited at the bottom of that slide, if you can see the slide, they will not have this restriction because they don't have 1 over k. Their k of xx is 1, so they don't have the k. But what they miss is they cannot really adapt to the target measure mu, and you don't see this universality of the asymptotic variance. But what they gain is that the weights are actually 1. And this actually allows them to relax the smoothness assumptions. And in particular, they don't have to control k at the border.
Okay. All right, cool. And then maybe a question that I have, just maybe a closing question. In this Monte Carlo integration setting, would there be any advantage to a non-symmetric kernel that allowed for attractive and repulsive interactions?
Yes, this is a very good question, and Yeah, possibly. I just don't know how to tackle it yet. I know RKHSs with non-symmetric kernels. Do we know a lot? Do we know anything about this?
It's not clear. A lot of the spectral assumptions don't really apply, right? Like maybe you could work with an SVD rather than Eigencomposition, perhaps.
This is a very good question. I mean, there's more and more of these. So there's a lot of repulsive point processes out there that are partly repulsive, partly attractive. And basically, so far we see how to make use of repulsion, but the attractive part, it's not completely clear yet. One example is if you leave DPPs, is the zeros of the planar Gaussian analytic function. So it's another way of defining repulsive point processes is to look at zeros of Gaussian processes, and you take the Gaussian process to be really, really smooth. So if your Gaussian process is smooth, the zeros will be far from each other. And so you will have if you manage to prove that your Gaussian process has isolated zeros, the point process will be repulsive. And you can actually cook up examples where you have local repulsion, but attraction in an annulus around the point. And that's actually useful, I think, for integration, because at some point you want to be repulsive. You don't want to have a neighbor, but if you haven't seen a neighbor in some characteristic length scale, then you need to put a neighbor. I mean, if you know that you have some information on the oscillations of the target functions, then maybe you have some critical length scale after which you want to put a zero. So you want to have attraction in an annulus. So you want to have local repulsion and maybe attraction in some range of distances between the points. So I think this is totally reasonable to expect that attraction could be useful as well. But so far, more than this intuition, I don't see any precise result.
Thanks.
You're welcome.
Thanks again, Rémi. Excellent talk.
Yeah.